Good morning, everybody. Today is our last set of notes for the semester. You're done with Math 114, so all you have after today is really to start preparing for the final. Keep in mind the final will be on Sunday from 4 to 6 p.m. I'll get your grades, I'll get those graded, and then I'll have everything posted Monday afternoon on EKU Direct. I'll try to get your grades updated in Infinite Campus Sunday evening. So that you know exactly where you stand. As far as what we're looking at today, we're looking at logarithmic and exponential equations. So it's just building upon what we've done the last 2 days. Not really introducing anything new, except for the last example where we kind of borrow an old trick that we used at one point when we were doing quadratic equations. So I'm just going to go ahead and jump into these examples. And the first one we're asked to solve this logarithmic equation. And we have 2 times log base 5 of x equals log base 5 of 9. We'll keep in mind one of the things that we learned yesterday is how we can interchange the way logarithms are written. So we notice on the left-hand side there's a 2 in front of that log base 5 of x. So let's rewrite this as log base 5 of x squared equals log base 5 of 9. And the only way that this statement can be true, we notice both sides have a log base 5. The only way this statement can be true is if the argument of both logarithms are equal. So we can just simply say that x squared is equal to 9, and then take the square root of both sides. And we get that x is plus or minus 3. And that's our solution to that example 1. X can be positive 3, x can be negative 3. One thing too to point out is that sometimes there can be extraneous solutions to logarithmic expressions, and one thing that we want to make sure that we are aware of is how to find the domain of logarithms before we proceed with the expression itself. So for example 2, we have this x plus 6. So remember, to check the domain of a logarithm, you always take its argument and you ensure that it is greater than 0. So for x plus 6, we have x is greater than negative 6. And for x plus 2, we have x is greater than negative 2. The larger of the two values always takes precedent. It defines the domain. Since x is greater than negative 2 is the larger of the two values, the domain for this entire expression has to be any x values that are greater than negative 2. And now we can go ahead and proceed with solving this. Since we have logarithmic addition, we can rewrite this as logarithmic multiplication. We have log base 5 x plus 2. And the x plus 6 times x plus 2, we can write that out as a quadratic. It'd be x squared plus 8x plus 12. And now we can get rid of our log by taking the base of the logarithm and raising it to the power of 1. I don't know why I changed that to a 2. So we get x squared 8x plus 12 is equal to 5 to the first power. We can simplify this, subtract 5 from both sides, and then now we can factor, and we get x plus 7 and x plus 1. And we know that the solution to this is x equals negative 7 or x equals negative 1. So we need to compare these two values to our domain restrictions. Our domain says that x has to be greater than negative 2. Only one of these values is greater than negative 2, so we can eliminate negative 7, and we know that the solution to the logarithm is that x is equal to negative 1. Example 3 is a very similar process. We need to first set up the domain restrictions. So for natural log of x, we know that x has to be greater than 0. For x plus 6, we know that x has to be greater than negative 6. And for x minus 4, we know that x has to be greater than 4. So once again, we look for the largest value. In this case, it's x is greater than 4, so that is our domain restriction for the entire function. And we can go ahead and start solving this using the techniques that we have. So first we have natural log of x equals, we go from subtraction to division, so we get x plus 6 for x minus 4. And again, for this statement to be true, the arguments have to be equal to one another. So we can just drop the natural logs at this point, x plus 6 over x minus 4. Multiply both sides by x minus 4. And then we'll subtract everything from the right-hand side to write this out as a quadratic. And we can factor this as x minus 6, x plus 1. And we know the solutions are x equals 6, x equals negative 1. So let's compare these two solutions to our domain restriction. Our domain restriction is that x has to be greater than 4. So negative 1 does not work in this set. Only positive 6 will work. For example 4, we're going to start taking exponentials and solving those, whereas we've been doing logarithms and solving. Now we're going to do exponentials, but we're going to do the same steps. We're going to actually convert these to logarithms, and the easiest technique is to simply take the natural log of both sides of the equation. We're not doing anything fancy. Remember, you've been told this ever since you started learning algebra. Whatever you do to one side, you have to do to the other. So if I take the natural log of one side, I have to take the natural log of the other, and I've not changed the value of the expression. But what I've done is given myself a method that makes this easier to solve. I can pull my exponent down front as a coefficient now. And then I can divide both sides by the natural log of 2 to isolate x. And there's my solution. X equals the natural log of 5 over the natural log of 2. That's an exact answer. If you type it in your calculator, you're going to get an approximate answer. So unless told to, leave your answers in exact form. Now with part B, we can still do the same thing, but what we need to do first is divide both sides by that 8. We want to get the exponential portion by itself. And then now we can proceed just as we did with part A of this example. So we can take the natural log of both sides. And bring the x down as a coefficient. And divide both sides by natural log of 3. And there's our solution. With example 5, we're going to do the same steps. This is going to be a little bit more in depth and involved than the previous examples, but the process is the same. If we take the natural log of both sides, I'm actually just going to go ahead and bring the exponents down because we're familiar with that step now. And I want to distribute what's in the parentheses to each one of the logarithmic terms. So what I have is x natural log of 5 minus 2 natural log of 5 equals 3x natural log of 3 plus 2 natural log of 3. Now, despite the way that it looks, we still treat it just like we do any other algebraic equation that we're solving. We want to collect all of our variables on one side. Everything else is on the other side. So I'm going to move this constant term to the right, and I'm going to move this variable term to the left. So what I have at this point now is x natural log of 5 minus 3x natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. In the two terms on the left, they both have an x in common, so let's factor that x out. And at this point, if I divide both sides by the quantity in parentheses, I will get x by itself. And that's going to give me x equals 2, natural log of 3 plus 2, natural log of 5 over natural log of 5 minus 3, natural log of 3. And again, we have an exact answer. You could type it in and get the approximate, but like I said before, please leave it in an exact form unless told to do otherwise. And now we're on to our last example. You can start shedding tears now. I don't know if it'd be joy or sadness, but this is the last example for college algebra. And in this example, this may not appear to be quadratic, but we will generate it to be a quadratic that is easy for us to factor. And we're going to borrow a trick that we learned many moons ago with a U substitution. So we're going to write that out here shortly. With this particular problem, the two values that have the exponent, we see that we can write that 4 as the same base as the exponent that we currently have. And what we can write out is that 4 can become 2 to the x, and then we're squaring that quantity, or actually, sorry, it's 2 squared to the x power, and that's going to be minus 2 to the x minus 12 equals 0. So with this first term, it's 2 squared times itself x number of times. Or we can actually write this as 2 to the x squared minus 2 to the x minus 12, 0. So we can interchange those. That doesn't change the value, because whenever you raise a power to a power, you always multiply them together. So it could be, or you raise the power to the power. So here we would come up with our U substitution. And we want to just say, let's let U equal 2 to the x power. So what we have here on this first term is U squared. Our base is 2 to the x squared. Then we have minus U minus 12 equals 0. We have generated a quadratic that we know how to factor. This quadratic factors into U minus 4, U plus 3. And now we can go back to our original variable, replace the U with 2 to the x. And the zero product property, we can set each factor equal to 0. And here we would get 2 to the x equals 4. And so we know that x has to be 2, because 2 squared is the only thing that will give us 4. And on this right hand side, we actually get no solution, because we cannot raise a positive number to any power and end up getting a negative value. So the only solution that exists for this one is x equals positive 2. That's it. We're done. The only thing you have to worry about now is the final. So please be studying. I will be available for questions today, tomorrow, Saturday, and Sunday until 4 p.m. Please look over this stuff. Be ready for the final. Everybody should know at this point what they need to get on the final, to get their desired grade. If you don't know, or you lost that message, contact me and I'll tell you again what you need to get. But for right now, just worry about studying for the final. I'll probably put out another video to address any questions that come up frequently. Probably Saturday at the latest, and just hope that everybody's doing well, and I hope that I do get to talk to you again soon. So everybody take care.